Welcome to lecture 13, Modern Processors. This is the last lecture of our course. This is actually, the classification or taxonomy of computer system proposed by the Michael Flynn in 1966, which based on the number of concurrent instructions, single or multiple, and data stream, single or double or multiple for parallel computing architecture. So they are four actually in the number. So as you can see, a single instruction, single data stream. So example is the uni processor, single instruction, multiple data stream, which is example are vector and array processors. And the third one is multiple instruction, single data stream, which is not commercially available. And the last one is multiple instruction, multiple data stream. The examples are, symmetrical microprocessor clusters and NUMA system. Okay, fit in this category. So let's we will talk one by one in detail about these data and instruction streams. Okay. So before going to these computer instructions model, I need to discuss or I need to tell you the basic model of computation. Actually, there are two model of computation for the computer system. One is called serial computation and the second is called parallel computation. In serial computation, any problem can be solved by dividing the problem into the discrete instructions, and each instruction executed by the processor one at a time. So this is the traditional way of computation for old computer, for Pentium 3 and Pentium 4. In modern computer, where we are now, in modern computer, parallel computing means that multiple CPUs are working together, okay, and they are going to execute the instructions, multiple instruction concurrently. So this is parallel processing. So parallel processing actually save the time, reduce the cost, and also the computation power also improved as compared to the serial computation. Okay, so now we will discuss the Flynn classification of the computer system. So there are four, as I told you. So first start single instruction and single data. So here you can see there is one processor and one control unit and memory. So this, you can say this is processing unit actually. So one instruction received from the control unit, and then one data stream operate from the memory. So the uni processor is the example of this computer system, like if we have one processor in our computer system. Okay, then we have single instruction and multiple data. Here you can see that we have one control unit and multiple processing units and one shared memory or internet connection network. So here one instruction received from the control unit to the processors, multiple processor, and then multiple or different data stream, okay, work here from the shared memory or interconnection. So one thing you need to know here, that each processor has local memory, okay, and the communication between the processor is through shared memory, okay, or interconnection network. Now here the third one is multiple instruction and single data. So multiple instruction received from the multiple control unit. So each processor has its control unit and get the instruction from the control unit and then operate on a single data stream received from the memory. So the memory is here, a single memory for all these processors. Here multiple instruction, multiple data, so multiple instruction received from the multiple control unit. Each processor had its own control unit and then operate on different data stream from the shared memory or interconnection network. Here I need to tell you that when this kind of MIMD shared the memory with the processor, then this is called what? Multiprocessing. And when this kind of MIMD sharing the internet connection, then this is called multi-computer. So multi-computer has again two types based on the physical distance. If the all processor are working together and close in a one building, okay, so then this is called multi-computer. But if all these processors are far from each other in the different location, or you can say at remote area or remote location, then this is called distributed system. Okay. So here again you can see this classification of the parallel processing, single instruction, as I told you, uniprocessor, and here single instruction multiple data stream is the examples are vector processor and array processor. So vector processor includes actually multiple pipeline modules with the arithmetic logic unit, and whereas in the array processor include multiple arithmetic logic unit which may or may not maybe include pipeline concept. So what is pipeline concept is basically pipelining is arrangement of hardware elements of the CPU so that its overall performance can be increased. So this is pipelining. So here pipelining can be used or cannot be used in array. But array processing is faster than vector. But vector processing is basically cheap, inexpensive than array processing or array processor here. Then we have this multiple instruction single data stream. So as you know that this is not commercially available because it has this model has limited the option, or you can say it has limited application, so that it is not commercially available. Then we have multiple instruction multiple data stream, as I told you. So two types: shared memory or distributed memory, tightly coupled or loosely coupled. And then you have in shared memory tightly coupled, we have again two types: symmetrical multiprocessing and non-uniform memory access, which is NUMA. You need to understand that what is the meaning of tightly coupled and loosely coupled. Why we say that shared memory is tightly coupled and distributed memory is loosely coupled. So the difference between tightly coupled or loosely coupled is that tightly coupled means arrangement where we are going to share the memory. So all processing elements, they are going to share a single global memory, and the communication between the all processing elements through the shared memory. Okay, so this is basically tightly coupled. Loosely coupled, and one more thing about tightly coupled is that hardware and software are linking with each other, and also the hardware and software, they are depending on each other. So for example, if one of the a system is not working in the whole the tightly coupled network, so if one system is not working, so we need to power off the whole the system to fix the issue, not that single element where we have the problem. But in loosely coupled, hardware and software are linking with each other, but they are not, hardware and software, they are not depending on each other. If there is a problem in the single unit of the whole system, so that unit where we have a problem can be replaced. So it will not affect the whole system, which is the distributed system. Okay, and this is loosely coupled. So cluster is the example of the loosely coupled the arrangement. Okay, so this slide, if you see, that is the same copy which I explained you already in the previous slide. So we just leave it. This is same which we already explained. Okay, we will go to the next slide. Now, symmetrical multiprocessing, that is the example of the shared memory, or you can say tightly coupled model. As I told you that multiprocessing is basically the use of the multiple central processing unit within the single PC. That is called what? Multiprocessing. So multiprocessing has basically two types. One is called asymmetrical processing and another one is called symmetrical processing. Okay, so in asymmetrical processing model, there is a one master and multiple slaves. So asymmetrical model works in the master-slave relation. So there is a one master which is going to control all operation of the system, and the slaves are basically controlling by the master. So the main operating system is executed by the master. You can say the CPU, and there is no communication between the slave. So, and they are going to do the task whatever the master CPU tell the slave CPUs, central processing units. Okay, so and all CPUs are not treated equally. Okay, but in symmetrical microprocessing, all CPU which are working together in this model, they are treated equally. They all can execute instruction. They can all run applications. Okay, and the communication between the central processing unit through the shared memory. Okay, and in other words, we can say that all processor can schedule. Okay, now as you can see that symmetrical multiprocessor is basically has standalone computer with following abilities, characteristics. Two or more similar, the processor can connect it by internal. So same for memory access time, for same for all processors can share IO devices, all processors can perform same function. As I told you, equally they are going to treat. And so system controlled by integrated operating system, and they can do many tasks over there. Okay, so here you can see the organization of symmetrical multiprocessing. So multiple CPU with their cache memory, and then they are going to share the memory, and this is the I/O system. So the communication between the processor through the shared memory. Okay. Next. Now here you can see single process versus two processors means you can say uni-processing versus multi-processing. Now here you can see the first one is one processor, single processor, and you have multi-processor. Multiple processors are running, process 1, 2, and 3. And here you see there is a concept of interleaving. So here you see interleaving is basically, you can say, is a way to make the system efficient and fast. Now here we can see this is time sharing system, and for example process 1 start executing, and during that time process 2 and processor 3 is blocked. So blocked means waiting. So at a one time one process can run on the single processor. So in second you see here, then when process 2, so process 1 will be blocked, and then process 2 running, and process 3 is still here, blocked, so waiting. So here you can see at a one time we are going to execute a single process, but as from the programmer view or from the user view, we see that multiple processes are running. Actually it is not like that. So one process at a time is running, but we are taking the advantage of interleaving. Okay, so here you can see that the process interleave with each other. That is, at a one time, one process is executed by the processor. So this is also called, the multi-programming, when the computer system running more than one process at a time. So like, for example, if you open Microsoft Word or Firefox browser or in your computer system, so both programs loaded into the RAM and they run one at a time, but it seems to you that they are running at the same time. It is not like this. Okay. Now here in second example, two processes are running. So as you know, this is the advantage of multiprocessing, that multiple process can execute at the same time. Now you can see here, at the same time multiprocessors can be run. So one process may be from one processor, one CPU, another process may be by the second CPU. Okay, so that is basically the time sharing system. Okay. So multiprocessor operating system design consideration. Okay. Now here, when you are going to create or develop operating system, so what are the parameters, or what are the things we need to keep in our mind when we are designing any operating system for multiprocessor? So these are the points which we need to consider when we are going to develop any operating system for multiprocessor. Now the first one is the simultaneously concurrent process. We know that at the same time multiple CPUs can execute the process. So we need to keep in our mind that the operating system should be facilitate the multiple execution for the processor, and for this purpose they need to allow, for example, they need to allow several processes to execute. So operating system should manage the tables, the memory, and all resources for the processor, because processor needs resources, maybe a CPU time, maybe memory. So it should be available, and also it should be avoid avoid, the deadlock or in any invalid operation. So the structure should be in such a way so that these problems can be avoided. Then scheduling, as we know that operating system has some scheduling algorithm, like first come first serve, round robin, priority algorithm. So we need to see how these multiple algorithm will handle the multiple processor execution from the multiple processor. Also synchronization, that how multiple processes they will synchronize with each other, because the order is very important when you are executing the processes. So there are two types of the processing, that cooperating process and independent process. So in cooperating processes we are sharing the memory. So when we are sharing the memory among the process in exceptional way, we need to know we need to care about the order of the execution of the process. So order is very important. So we need to see also this in the designing of operating system. Also the memory management here. In the memory management here, we see when we are going to manage the memory, we are doing paging, we are doing segmentation, so and so on. So we need to see that how these methods will work for multiple CPUs, how we can replace the page or segment. Okay, so how these algorithm will work to enforce the consistency among the processors. Then reliability and fault tolerance. So we need to also consider the reliability and the fault tolerance. Fault tolerance is what basically? The fault tolerance is actually the capability of a system that is works smoothly even if some problem happen. So without switching off or without stopping, the system should be work itself. Okay, this is a fault tolerance system. So we need to see also the reliability of the fault tolerance in case of the processor will not work, then how the operating system will fix the issue and how it will schedule the other task to fix the issue. Okay, if the processor does not work. Now clusters or clustering. As I told you that clustering or cluster model is basically distributed memory model in which each system has its own local memory, and the communication among the nodes through the very fast internet or network connection. So this approach is basically alternative to symmetrical multiprocessing. Okay, because of high performance and high availability. So high performance and high availability means that, as you know, that cluster is the combination of many standalone computers or nodes, and but they create illusion of one machine. So they are going to solve actually a very large problem. Okay, and high performance means that because not one machine involved to solve the problem, there are multiple nodes are going to solve the problem. So the performance will be increased. So computation time will be decreased and the performance will be improved. And also high availability means, for example, because multiple nodes are working together in the cluster, and these nodes are independent of each other. Means if there is a one node doesn't work, so it will not affect the whole service of the whole system. That it will not stop the whole system. Only the which node is not working cannot affect other nodes. Okay. Now, as I told you that in clustering, that each computer is called a node, and they are working together. They are going to communicate with each other through the interconnection. Okay. Now, there are some benefits of clustering. That's why we prefer the clustering over SMP. SMP is good for the small organization, and but clustering is a good way where we have a large organization and we have a very large big problem we are going to solve. But in clustering, one thing you need to know or remember, that in clustering we can use any model. We can use clustering as a shared model or distributed memory model. It's up to you. Okay. So there is no compulsion or mandatory that you use only distributed memory model. Okay. So these are the benefits of the clustering or clusters: absolute scalability, incremental scalability, and high availability and superior price and performance. So absolute scalability, or you can say with this benefit, we can create large clusters. So a cluster can be dozen of multiple machines. So increment scalability, or you can say additional scalability, is that we are going to configure a system in such a way that we can add new system to the cluster in the small increment. So which will improve the performance of the cluster system. Then we have high availability. As I told you, that if one of the node doesn't work, it will not affect the whole cluster system. It will not affect the service. Okay. So service will be carry on, because the other nodes will take over and can work for that node which is not working. Then we have superior price performance. So it means that because of the system improve the performance and availability, high availability, so that it is worthable to use clustering as compared to symmetrical multiprocessing model, because cost is reduced and also we get the more performance as compared to symmetrical multiprocessing system, because over there is a limitation of adding more processors. So there is a limitation in the symmetrical processor. We have a limit. More than that limit, we are not allowed to add more processor, because the performance will be decreased substantially. Okay. So this is the clustering computer architecture. As you can see, that we have different nodes, or you can say multiple standalone computer working together, okay, with high speed network. Now here there is a comparison of cluster to SMP. So one common thing in between clustering and SMP is that Both provide multiple processor to support high demand application. Both solutions are available commercially, okay, and it's up to the organization what they are going to use, SMP or clustering. As I told you in the last slide, SMP is a good solution for the small organization, and clustering is good for large organization. Okay, so here you can see that it is easier to manage, more closer to single process model, okay, or written, and we don't need multiple standalone computers or system. We're just using one system, and multiple central processing units can be added in this SMP, and we can work. So less power and less physical space and stable. Here in clustering, so what is the important thing in clustering is, or the best option is that in clustering we can increase the node. Okay, so we can increase the node, or we can scale up. But SMP has some limitation. We will discuss later in the next few slides about this. And availability, as I told you, because SMP is just a standalone computer with multiple CPUs, but here clustering is a combination or of multiple nodes or multiple standalone computers. So if one of the node is doesn't work, it will not affect the service. Okay, and all component system can be made highly redundant, means there is because all nodes can work. So that means we have highly redundant things we can get over there. Okay, so non-uniform memory access here, NUMA. So actually microprocessor can be, the multiprocessing can be categorized into three shared memory model. One is uniform memory access model, another one is non-uniform memory access model, and the third one is cache coherent NUMA model. So these three are the models of the multiprocessing with shared memory. So this is the NUMA is actually the alternative of SMP and clustering model. So first of all, we'll discuss what is uniform memory access. So in uniform memory access, all processors have access to all main memory parts. Equally they are going to treat, and access time of all region is same. So also the access time to the memory for different processors is also same. So that's why it is called uniform. So all processors treated equally in everything. So that's why it is uniform memory access. So symmetrical SMP is the type of uniform memory access. Okay, and also now here then we have non-uniform memory access. So in non-uniform memory access, this is same, that they can access all parts of the main memory using load and store, load data and store data, and then but access time of the processor depend on the region of the main memory is being accessed, and also the different process access different region of the memory at different speed. So as you can see here that in UMA single memory controller is used, and so it is slower, and in NUMA we are going to use different memory controller is used, so this is access is faster. So uniform memory access is actually using for time sharing application, and this is good for real time applications. Okay, the non-uniform memory access model. Okay, and the third one is cache coherent NUMA, which is in a system in which cache coherence is maintained among the cache of various processes, because there are multiple processors are working. So each processor has its own cache memory. So the cache coherence is required among the processor. So what is cache coherence? Cache coherence is actually a concept in which keeping the multiple local cache synchronized when one of the processor updates its local copy of the data, which is shared, among the multiple caches. So this is the third kind of the multiprocessing share memory model. Now, motivation of the NUMA. Why we need NUMA? Why we need to develop of NUMA when we have already SMP and clustering model? So one of the reason of or impulse of developing of NUMA is basically that SMP has some practical limitation of number of processor. So as you know that SMP is a standalone system where we have multiple CPUs are working together or processors are working together. So there is a point where we cannot add more processor, because if we add more processors, the performance will be decreased. So no benefit to add more processors. So for example, you can say that, for example, limitation is 64 processors. So in SMP model, we can add more than 64 processors. So after adding more than 64 processors, the performance of the system will be decreased substantially, so that this is the practical limit. So then we develop, or you can say the motivation for clustering model because of this issue. So then we develop a clustering model. In this model, you know that each node had its own private main memory. So again, we have facing some problem in this model. So what are the problems? For example, here that there is an issue of memory granularity. So because as you know that in SMP we are going to use or going to share the bus for communication between the multiple processor and main memory. So if we add more processors, so the traffic will be increased. Once the traffic will be increased, it will be burden on the system, and the performance will be decreased. So we jump to the clustering. So whenever we jump to the clustering, so we said that maybe the clustering will solve this issue. So whenever we jump to the clustering model, here we see that there are two issues are here. One is, the cache coherence is maintained, or in the software rather than in the hardware. So software will when the something is maintained by the software, it will take the more time. Too many computations will work, so it will slow down the system. And also there is a problem, as I told you, that is memory granularity. So memory granularity is basically is that uh, that if the amount of the data that sent which each update to the processor. So this memory granularity problem will minimize again the performance of the clustering system. And if we want to achieve maximum performance, we need to tell, or we need to familiar, or we need to see the whole picture of the global memory. So it means all application needs to see the whole picture of the global memory. Otherwise, it is difficult to achieve the performance. So then we jumped, or you can say switch to the another model, which is NUMA, non-uniform memory access model. Here what we did actually, that the basic model we adopt from the SMP, okay, and then what we add only here, that because in SMP we have the same memory controller, but here we are going to use a different memory controller in NUMA, and the access time of different processors to access the memory region is different. So it is actually improving the performance. So through NUMA we can increase the scaling. What was the problem in the SMP? That we have some practical limitation to add the processor, but here in NUMA we can add more processor, okay, but the structure, the architecture of the NUMA is taking the basic architecture we take from the SMP, okay. So in NUMA actually we have a transparent system to the the global memory, and multiple processor each had its own memory, bus or internal connection system. But if you see here in SMP, we have one bus link used for all processors. But here we see we use that each processor had its own bus link, okay, so that the traffic can be handled in a good manner, in a better way than SMP, okay. Okay, now multi-core computers. So there is a difference between multi-core computers and multi-processing computers. Multi-processing computer, that multi-processing computers are the computers or system in which multiple processors are working together, and they are executing the instruction concurrently, okay, to improve the speed of the system. In multi-core computer, multi-core computer basically, multi-core means it is a single processor with multiple cores, okay, or multiple, you can say multiple processing unit, more than one in the CPU. This is basically the multi-core computers, okay. So each core is consist of independent processor, register, ALU, and control unit, and there is also L1 level 1 instruction and data cache memory with this each core. But in the modern multi-core chips, they also include level 2 and level 3 cache memory, okay. Now here you can see the a view of multi-core computer. You see the motherboard. In the motherboard, we have one processor chip. In that chip, on a single chip, we have here, you can see multi cores, and each core has basically independent instruction logic, arithmetic logic unit, load store logic, and then we have two level of cache cache memory. You can see here level 1 and level 2, one for the instruction and one for the data. So here you see one level instruction and then one level for the data. Okay, so here you can see core 1, 2, 3 and multiple cores. This is the organization of multi-core computer. Now here you can see there are 4 types of multi-core organization. Here you can see. Now, so these multi-core organization depend on the 3 things basically. First, number of core processor on a chip. Number 2, number of levels of cache on the chip, and then third is amount of shared cache. Now you see in the first one, which is dedicated L1 cache, here you can see that in this organization, so only one on chip cache, there is only one level 1 cache on the core, on each core. You can see here. Okay, and then so the example is here is ARM11 MP core. This is the example of this dedicated L cache 1, and this is used basically in especially in the embedded chips. Okay, this kind of the organization of multi-core. Then this is the old one actually. Then you see the second one is which is dedicated L2. So here you can see that there is a main memory, and then L2 is dedicated to each core. Okay, so here you see that L1 and L2. Okay, so dedicate here. So the example is AMD Operaton, and the third one, if you see the share 2, now here you can see that there are using of 2 shared cache, and this is Intel core. And the fourth one, you see here use of shared L3 cache with dedicated L1 and L2 for each processor, and this is an example of Intel Core i7. So okay, so that's all. So next is what are the applications which are work effectively on the multi-core processors, or you can say the performance of these applications are brilliant if they are run on the multi-core processors. So these are multi-thread native applications. Example is Lotus Dominus Server program, and also multi-processing application like in the Oracle and SAP SAP, and also Java application which run Java Virtual Machine, Sun application server, etc. And also multi-instance application, one application running on multiple times. For example, in the computer system, if you hold the shift key and if you open any application which is on the system tray, okay, so multiple application you can open with this for example, if you have Microsoft Word, it is already open and it is on the system tray. So hold the shift key and then you can open multiple instances of the Microsoft Word application on the computer. So this is the example of the multi-instant application. Okay, and that is the end of the lecture. Our course has completed. So if you have any comment, questions, you can send to your concerned teacher and then he can answer to you. Stay safe and thank you for to listening me. Okay, goodbye.